This derivation sheet explores the relationship between a three-dimensional flow, known as a vector field, and a spherical boundary, demonstrating how the way the flow changes across space determines the total amount of stuff exiting the sphere, a concept called flux. The core principle: looking inside to understand the outside. To determine how much of a field is passing through the surface of a sphere, we can use a powerful principle that allows us to look at the source of the flow inside the volume instead of just measuring the surface. This principle reveals that the total outward flow is equal to the sum of all the tiny expansions or contractions happening at every point within the sphere. The role of symmetry and the power of the flow. The behavior of this flow depends heavily on a specific number used in its definition, the exponent or power. When the power is odd, the flow behaves like a fountain centered at the origin. Because the direction of the flow matches the direction of the points in space, every arrow points directly away from the center. This creates a radial field where the flow hits the entire surface of the sphere head-on, leading to a large, positive total flux. When the power is even, the flow becomes biased. Instead of radiating outward, all the components of the flow push toward the same corner of the universe, the region where all directions are positive. On a sphere centered at the origin, this creates a perfect balance. On one side, the flow is exiting, but on the opposite side, it is entering. These two sides cancel each other out exactly, resulting in a total net flow of 0. Visualizing the flow. Demos 1 and 2. To make these abstract concepts clear, we can use animations that map the flow as arrows. The arrow demo. In the first demonstration, you can see the arrows shift from a fountain shape, when the power is odd, to a skewed shape, when the power is even. The surface color demo. A second demonstration colors the surface of the sphere itself. When the power is odd, the entire sphere glows red, indicating a consistent outward push. When the power is even, the sphere is half red and half blue, visually proving that the entering and exiting flows are perfectly balanced. Example: what happens if we move the sphere? The zero flux result for even powers is highly sensitive to the sphere's position. The constant flow case. If the flow's expansion rate is the same everywhere, moving the sphere doesn't change anything. The same amount of stuff escapes the sphere regardless of where you put it. The changing flow case. If the flow gets stronger as you move further from the center, shifting the sphere breaks the perfect symmetry. The side of the sphere further from the origin will experience a much stronger flow than the side closer to it. Consequently, the cancellation that resulted in zero flux no longer occurs, and the total flux begins to increase as you move the sphere into stronger regions of the field. Interactive demo. Shifting perspectives. A final demonstration uses an interactive application with sliders to move the sphere around in three-dimensional space. As you move the center of the sphere away from the origin, you can watch the flux value jump from 0 to a positive or negative number, illustrating how the balance of a vector field is tied to its position relative to the center of the flow.